Welcome to this lecture on cryogenic hydrogen technology. So, today this is in continuation to our earlier discussion on cryogenic hydrogen production, hydrogen production in particular. And in the last class we have talked about certain hydrogen production technique, mostly those are based on the conventional energy resources, and we have talked about the steam reforming, then we have talked about the partial oxidation and autothermal process. So, today we will again look into those aspects in detail. So, let us go through this. So, this is as I told, this is in continuation to our earlier lecture on hydrogen production, and this is of course based on the conventional techniques, and the keywords are steam reforming, partial oxidation and autothermal reforming. So, if you remember in the last class we have talked about the reaction where steam reforming was taking place. We have said that the light feedstocks are there, and maybe it may be the methane, or it may be crude, light oil and naphtha, like that. And if it is the methane, that is the natural gas, one of the primary components of natural gas is methane. So, when methane is passed over heated catalytic bed, this is basically catalytic reaction, and it is endothermic in nature. So, we need to supply energy from outside or add heat from outside. So, this reaction is followed by the water gas ship reaction, where you will find that the CO and H2O are basically not in the form of ordinary water, it is in the form of steam, and this will give us CO2 and H2. So, the overall reaction, you will find that we are starting with the methane and the steam at elevated temperature, and it is a catalytic reaction, we have said. So, the catalyst is nickel, and if we are starting with say the methane and steam, and finally, we are getting CO and H2. So, that is hydrogen and CO, that is the carbon monoxide, this mixture will be obtained. Basically, this COH2 mixture is called the syngas. So, the first reaction we have already learned that this is endothermic. So, we need to supply energy, whereas this is exothermic, and it does not need any energy, rather energy will be evolved from here. But the point is that it needs a catalyst, and the catalyst is nickel, that is commonly used, one of the popular catalyst for this reaction. Now, this nickel is basically it is susceptible to certain gases or components which may be detrimental for nickel. So, the feedstock being natural gas, LPG or naphtha, etc., and these these are natural components, and it may always have some what is called sulfur and chlorides. Okay. So, these mercaptans and thiophene are the common the sulfur contents in this in this feedstock, and this sulfur content or chloride contents are not good for this nickel. So, they are not in good harmony. So, we have to first do the feed treatment, pre-treatment of the feed is necessary before we start this steam reforming reaction. So, this nickel catalysts are sensible to this sulfur and chlorides. So, we have to keep it in mind that before we start this reaction, we must get rid of these feedstocks, this sulfur and chloride. So, we need to clean this fluid from sulfur and chloride. So, let us look into this how it is done. So, in the process diagram. So, here is the feed, and the feed pretreatment is done. Let us look into this feed pretreatment. So, this nickel catalyst will be subjected to hydrogen. So, hydrogenation of this thiophene or the mercaptans will result in formation of hydrogen sulfide, and basically this mixture of hydrogen and the feed will be passing over the cobalt molybdenum catalytic bed, and this will generate the H2S. Finally, this H2S will be removed with the help of zinc oxide ZNO, and that will produce finally the zinc sulphate and H2O. So, this is how we remove the hydrogen the sulfur contents from the feed, or this is called the feed pretreatment, particularly necessary for the steam reforming. So, this will generate the treated feed, and this treated feed will be again now taken into the reaction. So, this is as we have learned that we need certain amount of hydrogen for feed pretreatment. So, we have to later on see where from this hydrogen is coming. So, we have done the feed treatment and pretreatment, and then it is coming to the reformer. So, this reformer, as we have understand that this needs some amount of thermal energy. So, this thermal energy will be given in the form of fuel burning, and not only that, we also need steam. So, the steam has to come to this process, and this is coming from the demineralized water. But this demineralized water we will try to initially do some waste heat recovery, that we will see how it is generating, and that demineralized water will be forming steam using the waste heat that is generated from this reformer. And finally, this flue gas, basically this reformer will generate certain amount of flue gas, that flue gas being at high temperature, we will try to utilize that and produce the steam using that energy, waste heat energy. So, from the reformer what we get is the syngas, basically a combination of CO and H2. At the same time, at the exit or at the outlet of this reformer, there would be parallelly water gas shift reaction. So, where you see the water or the steam H2 and CO will be further reacting to generate CO2 and H2. So, basically that will enhance the H2 content in the overall reaction. So, water gas shift reaction will take place, and finally, that will come to here what we have is basically CO plus H2. This combination would be there. Along with that, some amount of feed will also be carried over, as well as CO2 will be there in this reaction. So, all these things finally what we are looking for is basically from here, this is the hydrogen that if we want for our hydrogen production. Please note that this CO is again important for the chemical plants, and but particularly for this application here we are looking for the hydrogen. So, we need to get it and this is PSA is something which is called pressure swing adsorption, where this hydrogen will be separated and we get finally the hydrogen product. And as we have learned earlier that the feed pretreatment is needing some amount of hydrogen. So, that hydrogen will come from here, and this feed treatment will be done initially using this final product. A part of it will be delivered to diverted to the feed pretreatment. So, this is the one of the, or rather the process diagram for steam reforming. There are other modifications or modified versions of this will be available depending on the feed and its the COH2 content. So, here if we look back, we will find that the overall reaction for this I mean CH4 plus H2O, that is steam, that is generating some amount of CO plus H2, that is the what is called reforming reaction. So, this is steam and this is carbon. So, the steam to carbon ratio or the stoichiometry is basically 1. So, we have 1 carbon and for which we are giving 1 steam, but in reality what we will find that this ratio goes as high as 3.3 to 3.5, and the higher the ratio we will have more it will be shifting towards more hydrogen generation. So, if we are looking for more hydrogen, so we will try to put more steam in it, but at the cost of definitely more firing or the heat input to the system. So, we need to keep this in mind that we are putting additional amount of steam into the system, and that will basically help us to generate more hydrogen. But if it is so that you need this CO content more, and in that case this will be the steam content will be slightly less in quantity. So, this is what we have to keep it in mind. Fine. So, this is the trailing gas part. Here you can see that we have obtained this cleaned version of the gas is coming from here. So, this is the PSS system, and this PSS system has finally generated this hydrogen, but at the same time this is called the PSA tail gas. This will have some content of H2CH4, which we have not separated, or it is basically kind of forming a mixture, but it is having some calorific value. So, we will add it with the fuel, and that will be used as fuel gas, basically that will be combined with the fuel and it will try to heat up the system. So, that is about the steam reforming in short. So, now let us look into the reformer, how it looks like. Basically, as we have understood that this is having some catalytic bed. Let us look into this the radiation zone, what is called. So, here we have the the catalytic bed through which CO and H2O, that is steam, that is flowing in, and here we are these are the burners, these are the top fired radiation zone, and this reformer or reforming zone where this catalytic bed is formed inside this tube. And generally this CH4, I am sorry, this is not CO, CH4 will be flowing in along with H2O. So, that will generate CH4 plus H2O will come in, and it will form the CO and H2, that will be the product. So, here we have CH4 plus steam, and we are adding heat using the burners. So, this is the top fired one, then we have the bottom fired and the again side fired one, and there are different geometry, those are possible. But this methane generally we try to put it under pressure, because that will give us this H2 under pressurized condition, though the thermodynamics will tell that this methane at low pressure would have been better. But finally, as we understand that this hydrogen it has to be stored in a compressed condition, or it has to be liquefied. So, preferably we try to put it in under pressure, and that will generate the hydrogen under pressure. And but there is a limit to which we can put it under pressure, because these tubes are the tube has to withstand the high pressure at elevated temperature. And typically, if we look at the temperature at this point will be around, I am sorry, this is not visible here. So, this is coming out at around from the radiation zone, it is the convective zone. So, this is 850. So, I am sorry, this is 850 to 920 is the typical temperature at which they are coming. So, this is at that temperature this gas is going out, or the reactants are coming out. Finally, this is the kind of several, I mean this is only one tube has been shown. So, in reality you will find such multiple tubes are in use, and we will be able to get the I mean CO and H2 under pressure, and of course, at elevated temperature. So, this temperature, as I told you, that they are at high temperature around 850 to 920 degrees centigrade. So, obviously, they are to be cooled, and of course, that CO2 is to be separated, which is coming from the water gas shift reaction. So, those high temperature separation of CO2 and finally, separating out this H2 needs certain amount of cooling, and there this cooling of these gases finally will be I mean done by some waste gas recovery, where you will find that we are trying to cool them down using the water, and that water will eventually be used useful for generating the steam. So, that is how we try to reduce the temperature of these gases whenever necessary, and use it for generating the steam. So, now let us look into the partial oxidation reaction. So, we have also talked about it, and this is the summary of that partial oxidation reaction, where we have seen that this is the salient features of it is that it is a non-catalytic reaction, and this is exothermic in reaction. That means, we need not supply additional heat from outside, but what we need to supply is the oxygen. So, here this is the oxygen that we have to supply, and the feedstock is basically one of them could be it is not necessarily restricted to the coal, but we can also use natural gas as well as coal and heavy oil. Okay. So, we have to be careful about the use of less oxygen in the system, which may result from soot formation and its handling. So, but importantly what we understand is that we need some O2. Can we not use air? The answer is yes. So, we can use air instead of O2, because this finally this oxygen that is being used here will be separated from air only. So, it contains the air contains N2 and O2, and from this O2 only it will be separated maybe by say membrane separation or cryogenic separation, and that oxygen will be used in the reaction. But the problem with air is that if we are using air, this nitrogen will be staying with this reaction, and here whatever in addition to this what is called the partial oxidation reaction, if there is any additional CO or water gas shift reaction is there taking place, because some amount of water will also be added to this system. So, that will cause N2 will be added with that system. Finally, if we want to remove any CO2 from the system, and along with that this nitrogen will be there at high pressure, or NOx formation will also be more in quantity. So, that means later on, if we have to at all separate this NOx or N2, it is better if we separate this air initially and put it in the form of O2 in the reaction. That will be advantageous. So, let us now look how it actually this process is taking into action. So, this is partial oxidation. So, here we have another important part is that there is no catalyst are in use. So, non-catalytic reaction, so there is no initial pre-treatment is necessary. So, here we have heavy oil and we are putting O2, and that is the partial oxidation is taking place in that reaction zone, and from the reaction zone it is the syngas that is coming. This reaction is exothermic in nature. So, its the temperature would be quite high. So, nearly it will go as high as 1200 to 1400 degree centigrade, and there we will find that it needs quenching of the syngas. So, once we try to quench it, it is again we try to use the demineralized water to generate the steam. This steam will be useful later on, okay, for different purposes. Okay. So, this finally this syngas has to be again CO2 and H2O will be removed, and this CO2 concentrated CO2 will be coming from here, and it is most of the time it is removed from here, and this H2S that is being separated from here, we try to generate the sulfur from here, and that sulfur often is used for producing the sulfuric acid, another important component in the chemical industries. So, finally, what we do is that we try to condense it and generate the what is called, again it will be subjected to PSA to generate the hydrogen. So, this process takes place around, as I told you, that this partial oxidation it will be around 1200 to 1400 when it is coming out from this reaction zone. Now, we have talked about in both the processes something called pressure swing adsorption, PSA. Now, let us have a look into what is this PSA or pressure swing adsorption. This pressure swing adsorption is basically this PSA pressure swing adsorption is something where you can understand that pressure swing adsorption. There is another process called absorption, but here what we have written is adsorption. So, adsorption means there are adsorbents which will adsorb some of the gases selectively. Adsorbent like most common adsorbent, if you are familiar with maybe the silica gel. Silica gel is some adsorbent which you are familiar with when you buy some costly instrument. You will find there is a small sachet and it is having some salt like structure. Basically, that is very often it is silica gel to absorb the moisture. So, there after some time they will absorb the moisture or retain the moisture, but after some time these internal pores, basically these are porous material, these adsorbents. So, these pores will be saturated with the what is called, if it is for H2O or moisture, this will be absorbing this moisture and finally, it will be saturated. So, after some time you need to regenerate it, you need to reactivate it, and one way of reactivating it is basically to enhance its temperature. So, that is what is called the temperature swing adsorption, where you are at some point it is at low temperature or at room temperature, they are absorbing the moisture or the the adsorbate they are absorbing, and later on they are also they are releasing it by change in the temperature. So, that is what is called the thermal swing adsorption, but in contrast to that we have the pressure swing adsorption. So, at some point the adsorbent bed will be pressurized, this this gas from here, this mixture, this is called the raw hydrogen will be coming from here, and this raw hydrogen will pass through that adsorbent bed. Many a times this is activated carbon or some other adsorbent would be there depending on the impurities which is there in it. So, this bed will be finally saturated with those impurities, and that bed will be again reactivated by depressurizing it. So, that means it is a intermittent process where you will find the successive pressurization and depressurization is trying to purify this raw hydrogen, and from there we are getting the pure hydrogen. So, that is about the partial oxidation, and now as we have learned the third one, that is the autothermal reforming, where you will find that the natural gas and steam may beat up it sometime we add these two, and finally, this O2 or air is getting mixed with it and they are coming to this combustion zone. So, this is where you can understand that this is basically the process is PO or partial oxidation that is happening, because here we do not need any additional heat input, but whereas here we have the catalytic bed and this mixture is coming over here, and here that steam reforming is taking place, and that steam along with that what is called that reactants of PO will be forming the finally CO plus H2 combination, and this syngas will be coming out at a moderate temperature. Since we are not adding any heat from outside, you will find that the resulting temperature will be something like 900 to 1100. So, that is about these three processes. So, let us try to have a comparison of these three processes that we have learned so far, that is steam reforming, partial oxidation and autothermal. So, what are the advantages of this steam reforming process? So, it is having it is extensively in use in the industrial scale, and we have lot of experience of handling it in the industries, and of course, there is no O2 requirement in the steam reforming process, but it is we need a catalytic bed. So, that is basically will come under disadvantage part, and relatively lower temperature among these three processes that we have seen, and it gives you the best H2CO ratio. So, if it is for the hydrogen production, definitely it is giving us the added benefit. On the other side, this is the highest air emissions it will have, and on the other part, I mean if we talk about the partial oxidation, we have decreased desulfurization, that is the feed treatment initially is not needed, and there is no catalyst of course, but this partial oxidation will need the oxygen supply, and relatively on the disadvantage part we find that it has a low H2 by CO ratio, and of course, as we have learned that its temperature is quite high, nearly about 1200 to 1400 degrees centigrade. And here on the advantage part is that we have written the low methane slip, that means methane content in the reactant or in the final product will be much less. In the autothermal process, of course, on the other part, the soot formation and its handling is a disadvantage on the partial oxidation part. In the autothermal process, we see that there is low temperature, relatively low process temperature, and it is also having the advantage of low methane slip. But on the other side, it needs O2, which we have also said in case of partial oxidation, because that will additionally cost the separation of air will be coming in play. So that's about this salient features of these three technologies for generating hydrogen. And the references are like this. We have this industrial gas processing edited by Herring and A. Leon for hydrogen technology, and this is a journal paper you can refer to. So, the conclusion, we have learned about the so called conventional techniques, the process features of this steam reforming, autothermal and partial oxidation. So, in future whenever needed, we will talk about these processes. So, you have to keep it in mind, the typical temperature range and the what are the basic needs of this kind of processes. So, that is about this hydrogen production at the moment. Thank you for your attention.